So in this particular example, the molecular formula of the compound with this spectrum represents is C8H10O. And we see the same thing that you've seen from the previous ones, that we have an aromatic ring because there are peaks in the aromatic region of the spectrum between 6.5 and 8. And I can see here that I have two doublets, and you'll see the doublets very clearly here. Now, these coupling constants that you'll find, if you had to work out what the coupling constants are, they are about 8 Hertz. Normally in an exam, I would either give you the coupling constant of the doublets, or what I would do is give you the individual peaks, and you may be required to calculate the coupling constant based on what I taught you about how to calculate coupling constants using the ppm scale that you see here. So I showed you an earlier example where the coupling constant between orthoprotons was 8 Hertz, and that 8 Hertz actually represented two protons being orthocoupled. So now I have two doublets, which means that I have orthoprotons here. So if I have orthoprotons here, this would give me a coupling constant of 8 Hertz. So I have 4 protons in this spectrum, so I must have a symmetrical structure because I only have 2 peaks. So there must be some symmetry down this line here, and this is also around 8 Hertz because both of the doublets have, you can see here, the same coupling constant. So one must be due to these two equivalent protons. I can call them A and A, and the other must be due to another two equivalent protons. I can call them B and B, which means that I have another group here and another group here. This pair of doublets on an aromatic ring is very, very typical of a para-disubstituted, and I say para-disubstituted because I have two substituents, so di-substituted, and they are situated para to each other. So we call this system a para-disubstituted system, and very typical of this system is a pair of doublets in the aromatic region of the spectrum with coupling constants of about 8 Hertz each. So I have a C6H4 fragment. I have two other peaks here, and if I now take my C8H10O and I subtract it, I find I have C2H6O, which means that I have another 2 carbons, and I can see those 2 carbons quite clearly here. This integrates to 3 and that integrates to 3, which is very nice because relatively this is a CH3 group and this is also a CH3 group. You see, none of these two CH3s are in the CH3 region of the aromatic spectrum, so something must have happened to both of these CH3 groups. I know that they are CH3s because they integrate proportionally to the 4 hydrogens on the benzene ring. Right, so if I use my integration here and I measure the height between there and there, that proportionally is 3 parts to 2 parts. So I have 2 CH3 groups. Now something must have happened more to this, de-shielded this methyl group much more than that methyl group. And remember, when we de-shield resonances with atoms, especially electronegative atoms, they move around 3.4, 3.5, closer to 4. So on this methyl group here, I must have an electronegative atom. If I look at my molecular formula, I just have an oxygen atom left. So I can bond the oxygen atom to that CH3. So I can have this fragment. So I look at all the fragments that I have. I have this aromatic ring. I have that fragment and that fragment, and these two fragments C2860 correspond to what was left over. So I got to put this OCH3 and the CH3 at these two positions, and it doesn't really matter at which position I put them because it would be the same because the molecule is symmetrical. So I can put the OCH3 here and the CH3 on that side, and I would have the structure for this molecule C6H8, C6H10, 3, 6, 7, 8, 9, 10, O. If I go back and analyze this, I have a structure here where this should be a singlet that's de-shielded. It's a singlet because it's not next to any other protonated group. So that 3 proton singlet should be de-shielded somewhere around 4, and that's the singlet I have here. And now the CH3 group that I have here is also de-shielded by the aromatic ring. That's why it's around 2.2. And it's also a singlet that's not next to any other proton group, and my aromatic ring, which I have ortho protons that are coupled. You can see it here, and this is the structure which makes sense for this particular spectrum.